size gate. Okay? Its dimensions are given there. We have a 2 meter wide and a 4 meter tall rectangular gate is pitched to the pivot about the point 1. Okay? So point 1 is a pivot. So this gate can actually open and close this way. Okay? Open and close this way. Determine the magnitude and location of the resultant force exerted on the gate by the water of the tank. So this gate here is acted on by forces in the water, and so in other words, these forces will vary, increase as you go deeper and deeper into the water. So there is a resultant force. We can consolidate all these forces and say that, okay, all these forces can be consolidated, become the resultant force acting on the gate. Okay? And then next we have to find, okay, where is this point here where the force is acting. Besides having to find the magnitude of this force, given gamma of water. So how do we go about doing that? How do we start? That means first we need to find FR, the magnitude of the resultant force. Magnitude of the resultant force, FR. So what is FR? Any suggestions how to get started? It's very important to examine the diagram and to look at the question very carefully. Okay? So the gate width is 2 meters and its height is 4 meters. And distance of the top corner of the gate, from the water level is 6 meters. Okay? And distance of the bottom corner of the gate from the water surface will be 6 meters plus 4 meters, which is 10 meters. Okay? So then, let's apply what we just learned. How to find FR? So for first part, FR is equal to gamma sine theta integral over the whole area of the gate times YdA. That's what we have got just now. Okay, so this is equal to gamma sine theta. Okay, these are all constants, that's why they're outside the integral. So this becomes, so YdA is Y, what's dA? dA is d times dy. Okay, over y. Because we are going to integrate across the y direction. That's where the forces vary. In the horizontal direction, there's no, the forces don't vary. The forces only vary in the along the y direction because forces vary with that. So what is B then? B is the width of the gate. The width of the gate is given as 2 meters. Okay, so we're going to take out B We will take out D here, and we will put it in the front. 2, that's our D. We put back the gamma times sine theta, and we will integrate over the whole length y. Okay? So we have y dy. So y, we can integrate across y from what value to what value? So this is the gate, okay, and water level is up there. Okay, the forces vary. We're going to find the resultant force. Right? And because all these forces acting along this, the whole surface, horizontally there's no variation, it only varies in the y direction. So then when you integrate across y, you have to go from the top edge of the gate to the bottom edge of the gate. Top edge to the bottom edge. Where is the origin? The origin is of course at the water surface. So we integrate across y from the top of the gate to the bottom of the gate. Okay? Referencing from the origin as the water surface. So in this case, y will go from 6 meters, that is the top of the gate from the water surface, all the way to the bottom part of the gate, which is 10. Okay? 6 to 10. 6 to 10. So then you put in the value. 2 is there. What is gamma? For water is 9.8 times 10 to the power of 3. What is theta? Theta is 60 degrees. Okay. And then you get evaluate y dy. Okay. I skip a few steps here. You should get 100 minus 36 over 2. Good. I'm sure you know how to get this. And use a calculator. It should give you 5.43 times 10 to the power of 5 Newton. So that is your SR, the resulting force acting on this gate. Resultant force acting on this gate. Okay, that's FR. Then next, where does this resultant force act? In other words, before we have learned, we'll find YR. What is YR? What is the YR? So your YR, this will be your YR. Okay? YR. So we apply the formula that we just derived. YR is equal to gamma sine theta integral of y squared dA over FR. Okay, that's what we have derived previously. So, in the same way, we can rewrite it as gamma sine theta integral of y squared, and dA is d times dy as before. D times dy. Okay? Then we integrate over the distance y over FR. So this was integral over A, now it's over y. Okay? So as before, E is equal to 2. So we bring the D out, D is equal to 2, bring out 2 gamma sine theta integral over y squared dy over f r. So just as before, you just carry out the integration, and let me just rewrite this. This is equals to 2 gamma sine theta. So again, you integrate across y, you be from 6 meters from the origin to the 10th meter point from the origin, y squared dy over f r. And if you do that, I skip the steps. From there to there, I'm sure you can do it. You put in all the numbers in there, it will give you 8.17 meter from origin. Origin is water surface. Okay, answer. Okay, I leave you to work out the arrow. The arrow, then you work it out yourself. Simple trigonometry and simple calculus. Okay? Now, okay, so that is the basic example to determine the resultant force acting on a submerged plate and the location where it acts on the plate. So that was a flat plate. Why if it's not a flat plate? It's a curved plate. What is a curved plate? Or a curved surface? Like a ship's hull. So in this case, things get a bit more complicated. Things get a bit more complicated. More challenging, more challenging. And okay, let's look at an example how we can apply what we also just learned onto a surface that is curved. So this is what you see here. This is part of ship's hull. This is part of a ship's hull. Okay. So you have water here, and there's no water on this side. So therefore, forces come into play, okay, which will keep the ship afloat. Or else, without these forces, the ship will sink because of this weight. So let's look at this example here. You have find the resultant force acting on the curved surface AB. So the curved surface AB of a ship submerged in the water as shown in the figure below. The curved surface is 1/4 of a circle of radius 1.5 meter. So this curved surface is a quarter of a circle. Okay? Radius is 1.5 meter. Now let's continue. The ship's length is 10 meter. So the ship, this is the curved surface, so the length of the ship, curved surface, the length of the ship is 10 meters. Okay? So it's not a very big ship, small ship. And it is 5 meters under the water. See the 5 meter here under the water. Okay? So also find the location of the horizontal and the vertical forces. So there are 3 things here as you analyze the question. First, you must find the resultant force. So where is the resultant force? This is the resultant force here, Fr, F resultant. Okay? And then you also need to find the location of the horizontal force and also the vertical force. So the horizontal force is Fx. Okay? And its location of that Fx. And also the location of the vertical force, which is Fy. So make sure when it comes to exam question, you study the question carefully. Don't miss out any part of the question. You miss any part of the question, you can't get marks for it. Okay, so, right. So how do we go about doing that? Okay, find the resultant force FR. Resultant force FR. How do we get started? Let's do A. Yeah? Find FR. No, nothing there. Okay, find FR. So how do we start? So you can see that the horizontal component force acting on AC. In other words, you can say F, okay, that's Fx, which is this horizontal component of SR acting on surface AC. Okay? And this surface AC is a straight line, Fx. So from what we understood from a flat surface, what do we see? This is equal to gamma sine theta, because AC is placed as a flat surface. Okay? You integrate over the area of that flat surface as y dA. Okay? We start from the flat surface first, AC. So what is theta in this case? For AC, what is theta? Theta is 90 degrees. Okay? Theta is 90 degrees. So, so that is equal to, we know gamma for water is 9.8 times 10 to the power 3, that is standard. And we have sine of 90 degrees. You know what is sine of 90 degrees? Then again, you integrate in this case, we have y, and have a b here, remember, we have a b here. Now this b is given, is the length of the sheet, is 10, as a b and dy. And now you don't integrate over the whole surface area, you integrate across y. Okay? Across y. So you go to evaluate this, you would get all the numbers, you can just use calculator. So all the numbers will give you 98 times 10 to the 3, because sine 90 degrees is equal to 1. Okay? So 9.8 times 10 to the 3 times 10 becomes 98. This 98, not 9.8, it's 9.8 times 10, give 98. Okay? Then integrate. You have across y, the body y. So now, what are the boundaries? What are the boundaries? Integrate from where to where? Must get this right. You don't get this right, the rest of the calculation will be wrong. But then, to where? What are the values? You go from, you're going to go, as you integrate, just for the flat plate, these are the previous flat plate rubber. Integrate from this point here, A, to point here, C. Okay? A to C. So what is the y value at A? At A. A is actually 5 minus 1.5. Okay, let's put here. 5 minus 1.5. Okay, to point C. Point C is what? Point C is 5. Okay? Point C is 5. So, okay? From 1.5 minus 1.5 at point A to point C. Point C is 5. As measured from the water surface, the origin. Just like what we've done for the flat plate. So I'm sure you know how to do the simple calculus. That will give you 6.2 meganewton. Okay, that is your Fx. 6.2 meganewton. Now, you need to consider Fy. Because Fr is the resultant. You know in your mechanics, in the 40 days of mechanics, or in the mechanics materials, to find the resultant, you must find the forces in the x direction, forces in the y direction, and then you do a Pythagoras theorem evaluation. Then you can find Fr. That's what we are trying to arrive at. Find Fx first, then find Fy. So next, we find Fy. So what is Fy? What do you think is Fy in this case? Fy is actually the weight of the water contained. Weight of the water contained where? It's the weight of the water contained where? Contained where? So Fy must balance, because floating must balance, because outward force must equal downward force. For object we balance. Okay? So Fy is equal to the weight of the whatever is on top. And what is that whatever is on top? Weight of the water, because this is must be equal to equivalent to weight of the so it has to be equivalent to the weight of the water contained at block ABBE of the ship. Okay? Weight of the water contained in block ABBE of the ship. So, in this case here, so in this case here, Fy is equal to mg, weight of water contained in block ABDE of the ship. Okay, equivalent, like that, as if there's water there, because it has got to balance. So that is equal to rho times the V times G, rho. V is the volume. V is the volume. So what is rho V? Rho V is actually gamma. Rho G is gamma. Rho G is gamma. And what is the volume? Volume is simply area times the length. Okay, area times the length. So it's the length, we call it h. Okay, don't be confused. This is just notation. Sometimes we use h for height, sometimes we use h for length, but don't you know what it is. H is the length times the area, cross-sectional area. Okay, and that would be equal to, what is gamma for water is 9.8 times 10 to the power of 3 Newton per meter cube times the length, h is the length. What is the length of the ship? 10 meter. Okay? Next, what is the A? A, no space, I put it here. What's the A, you think? I put a big bracket there. Yes. What's the A? So that curve here is in cross section. So what's the volume? What's the volume there? All the way. The cross section times the whole length of that sheet. So what's the volume in this case? Okay, so that can be cut into, can we cut it into two? Can we consider here, this one, which is a rectangle, okay, cross section is rectangle times the length of the sheet will give you the volume, okay? So that's a rectangle. Then after that we consider this curve here, 1/4 of the radius. So we break the volume into two different volumes, two volumes. One is rectangular in shape, one is a quarter of a circle. The volume pertaining to a quarter of a circle. Okay, so rectangular volume, this is easy. It's simply what? So this is a circle, quarter of a circle, you know what it is. Rectangular, the volume is simply H, which is already out there. And what's the cross-sectional area? Simply 3.5 times 1.5. 1.5 times 3.5.
Sir!
Okay. 1.5 times 3.5. That's the cross-sectional area times the length of the sheet. The length of the sheet is taken out already in the bracket here. That's the length of the sheet. Okay. So that gives you the volume contained in the rectangular sheet portion. So what about the quarter or the circle, the volume? This is simply what? Pi, actually it's quarter of a circle we are told. So quarter of a circle is simply pi r squared over 4. Things are revealed to you is that wow, great, if it's not revealed to you, wow, very tough. Pi r squared over 4. Okay? Quarter of a circle. And then times the length of the sheet that will give you the volume contained in that pertaining to the quarter of a circle. So with that, you can therefore determine your fx, your fy. So fy is therefore equal to 6.8 meganewton. Okay. So fx is 6.2 meganewton, fy is 6.8 meganewton. So therefore, what is the resulting force, Fr? So therefore, resultant force, Fr, is equal to square root of fx squared plus fy squared. I'm sure you know this, Pythagoras theorem, for determining the resultant given the x component and the y component. Okay. So therefore, if you do that, you get 9.2 meganewton. That is your answer for the resultant force Fr. Okay, use the calculator. 0.68 is it? And 0.62. Okay, that could be, I'll check, it could be a decimal displacement. Even 0.62 and 0.68. Anybody got also 0.62 or 0.68? Okay. Then let me just check this. Alright. Anyway, the method is there. Okay, maybe sometimes, eyesight, human error of the calculator. Maybe human error. I'm wearing progressive length. Okay, so you check. So if I do check also, I will check also. It's a matter of just what decimal point. But the approach is that Of course it's there. All right. So next, let's look at the location. For the location, we will have to go further. Location. So the location of Mx. Location of Mx. Location of Fx. Let's call it y. Let's call it y. Let's call it y. Okay. And it's equal to, from what we have got earlier, for location, when obtained that is equal to gamma sine theta integrate over the area A, y squared dA over Fx. Okay? And again, in the same way, we're going to convert this dA into the length times dy. So, that will give us gamma sine theta integrate across y and the y squared h length times dy. Okay, this is length of the sheet times dy over Fx. Okay, and so in this case here, what we integrate across what length? We integrate across what length? We know sine theta is 1, because theta is 90 degrees. Okay? So you take out a 10, becomes 10 gamma, and sine theta equal to 1 because it's 90 degrees. So integrate across y, the y squared dy, and what would be the boundaries be? There to there would be 3.5 to 3.5 to 5. So it's 3.5 to 5. Okay. It's from point A to point C. Point A to point C. Okay. And you have got Fx. And if you do your calculus correct, okay, and evaluate everything correctly, okay, I'm using Fx using this decimal point displacement. I follow my about, I check it out. So what I've got is 4.3. Okay, using the Fx that I got earlier. But anyway, these are all, some of my eyesight not so good. I will check it out, but the method is there. The method is there, just one decimal point. Okay, so I will check. So it's 4.3 meter below the free surface. Below free surface. Okay. So now Mx is acting at 4.3 meter below the free surface. So it could be error, some error there. So I just have a question mark there, but next week I will confirm this. Just decimal point because of Fx. So likewise, for location of Fy from position P, location Fy from position P, we will have so location of Fy from position B. Okay, this is from position B. That's how we locate our Fy. Must be from some reference. Because it cannot be from origin anymore, because this is a vertical force. From position B, okay? And let's call it X. Okay? Fy from position B. We call it XB, XB. So we know it's from B. So if that's the case, how do we continue from there? Okay, maybe instead of putting XB, we see location of Fy from position B. Okay, that's it, X. Therefore, given by, in this case, now if there's XB, that will be XB times the area of the circle. Instead of putting equal there, let's put this equal, let's put the bracket there. Okay. Would be XB times the area of a quarter circle. Let me just put it in words, so it's easier for you. Area of a quarter of a circle plus area of rectangle. Okay, put it in words first. It's given by this one, is given by XB, is area of quarter circle plus area of rectangle. And that, when I put the equation here, this will be equal to center of gravity of the area of the circle. Okay, the CG, center of gravity of the area of a quarter circle plus center of gravity of the area of rectangle. Okay, put it in words so that it's easier to understand. So then, we write some equation of put in words first so you know what is symbols are. So we have XB here. What is the area of a quarter circle? Area of a quarter circle, as we know, is pi r squared over 4. Okay? And what is the radius in this case? Radius is 1.5, and square it, divided by 4. Okay? That's area of a quarter circle, pi r squared over 4, plus area of the rectangle. In this case, the rectangle there is simply 1.5 times 3.5. Okay? Rectangle area. Okay, 1.5 times the 3.5. So 1.5 times 3.5. And equal to the right hand side, which is the center of gravity of the area of a quarter circle. What is the CG for the area of a quarter circle? Now, the CG location for a quarter circle is actually 4r over 3 pi. So 4r over 3 pi. Okay? distance of the center of gravity, okay, from any of the straight, from any of the horizontal and vertical lines is equal to 4r over 3 pi times the area of a circle times, so I continue, times what? Times pi 1.5 squared over 4, pi r squared over 4, then plus center of gravity of a rectangle times area of rectangle. So center of gravity, distance of CG from the side, relevant side of the rectangle times area of rectangle. So it's 1.5 over 2 because it's at the midpoint of the rectangle. 1.5 times the 3.5. Okay, so whatever CG here, it refers to the center of gravity of the water circle. In other words, if you have this, okay, this center is a water circle. Where is the CG of this water circle? The CG of this water circle, this is 4r over 3 pi. This is also 4r over 3 pi. R is the radius. So in this case here, all are known except xb. So therefore, using your calculator, your xb is actually, okay, because I have used previous values, so I have to check this number also, but that is the method. From position B, okay, from position. So I will check this number, I'll get back to you next week because we mix up the decimal point, I'm not sure it's an error, and decimal point, and go all the way down to use the values that you got before, so you get some error downstream as well. I will check, but this is the method. Okay, this is the method. So if you understand this, I try to go through this very slowly. If you still don't understand, you go back and go through this a few times. It becomes clearer. Of course, if you still at all, you can come and ask me. My email is on the is available, and I'll give it to you.
That's all.
Okay, so we found value FR, we found location of the horizontal and vertical components of FR. Okay. All right. So the example of dam. Okay. So dam, basically what's the purpose of having a dam? Is to produce hydroelectricity using water power. Okay? Water power. The power of the waterfall coming down from the height is very, very great. And you can use it to turn the wheel, turn the turbine, and rotation. The kinetic energy from rotation of the turbine can be used, converted to electrical energy and stored in the grid. Okay? So now for this one, before I do, I just give you the guideline, and you can go back and do this yourselves. I've gone through very slowly the 2 or 3 examples already. So let's look at this very quickly. We have here a 5-meter long concrete dam. Okay, a 5-meter long concrete dam. It's retaining a 10-meter, retaining 10 meter under the water, as shown in the figure. So 10 meter under the water is being stopped there. Okay. Find the resulting force exerted on the dam by the water. So find the resultant force exerted on the dam by the water. Okay. Find also the location of this force. Right? So find the resultant force. Define FR. Find FR. And also the location of this force. So I just give you some guideline because of time constraint. So similarly, you have to start. To find the resultant force, of course, you need to find Fx, then you need to find Fy. So you need to find so need to find firstly Fx, okay, then you find Fy, then Fr is simply square root of Fx squared plus Fy squared. Okay. Now the answer I've got here is, you can check it out, 2463. I hope there's no problem with calculator. I think you get the decimal point problem. Okay. That is the resultant force. So Fx, again you use it, gamma sine theta. Okay. You don't read the blank. Integral over the whole surface A. Y dA. Okay, and for Fy is equal to rho d d. D is the volume, okay, to the volume. Okay, and then you just calculate. So it's simpler. It's the weight of the water wedged in that rectangular column. Okay, and now, so then you find the location of this force, location of Fr. Where is the location of Fr? So location of Fr, location of Fr is quite wide, would be again equal to gamma sine theta, okay? Integral across area A, y squared dA over Fx. Okay, so what is the length? Where's the length? This is your, so you have your, so this is right here. This is equal to the length is 5. So take out the length 5 becomes 5 gamma sine theta. So integrate from where to where? That's always an important decision to make. Integrate from where to where for this dam. What is the, because the dam protrudes out of the water surface, so integrate from origin, which is 0, to the bottom of the river. So to 10, 0 to 10, your 0 boundary is very important. Okay? So integrate that, you should get your location for Fx. Okay? And then you find location for Fy, location of, put R there, it's Fx, Fx. The location of Fy, how to find? From where? This should be from D, from D, okay? Fy from D, So how do you go about doing it? Would be, maybe call that distance, so you call it xg, for example. So you set equation xb times area of rectangle okay, is equal to center of gravity, distance of the center of gravity from one side of the rectangle times the area